All right, so we'll move forward into linear models. In other words, it's bivariate data. Um, if we kind of start this conversation back in, I believe it was 1986, a lot of us are very familiar with the Challenger explosion. And this is some data that the NASA researchers did with a particular O-ring that ended up being the reason that the Challenger exploded. Was a O-ring malfunction. So they had done quite a bit of research. You can see where there's very little um, trouble with their O-ring with a lot of these temperatures from the mid 60s up to about 80 degrees. And then as it got cooler, you can see there started to be some failure. I'm not quite sure what this y-axis over here, I'm not sure what this is in terms of a unit, but apparently there was more failure as it got a little bit cooler outside. Well, the issue for these guys was the day that they um, launched, it was 31 degrees outside. And notice this says forecasted. So they were basically under the impression, hey, it's going to be just below freezing. And one of the issues here is 31 degrees is down here. The NASA researchers, they didn't have any data to kind of back up what they were doing at this point in time. They went ahead and launched anyway, assuming that this was a linear relationship. And then we obviously know what happened in the end. If they had done a little bit more research and been a little bit more thorough with what they were seeing, this actually ended up being more of an exponential model than a linear model, and but a little bit too late when all was said and done. So we're not going to be doing that kind of stuff in terms of big time research for NASA. What we're going to do is basically just kind of analyze scatter plots and take a look at what we're creating them and then analyzing them, a lot like we did with the univariate data with box plots and stem plots and whatnot. So basically what's happening with the scatter plot is now we're going to be taking a look at two quantitative, right? Before we looked at a single quantitative or maybe a single categorical variable, but here we are with two quantitative variables. Two terms that we need to know, explanatory variable is the x, right? So explanatory variable in this particular example would be powerboat registrations, and you think about it, what this graph is basically trying to take a look at, does the number of powerboat registrations, is that the explanation for this response in that manatees, the number of manatees that end up being killed? As we look at this in terms of analysis, what we want to do is look at the overall form and the deviations within the data. So first thing to look at, is it linear, is it not? Could you draw a line with some, feel pretty good about drawing a line through that? If you see anything that kind of jumps out at you in terms of um, like a deviation or maybe an outlier, this is a good place to put it. Maybe we mentioned right here, there's kind of a big cluster of data right there. That might be worth mentioning as well. Um, so the first thing, is it linear, is it not? The next is the direction of the association. So here we got a positive association, and then you want to discuss the strength. And when I'm saying discuss, it's literally just mention, is that a weak, a moderate, or a strong relationship? So a couple of examples. Here's one, and the explanatory variable for us. The x would be the number of bikes in use, followed by the response variable, the number of accidents. The form, I can see this does look very linear, and maybe a possible outlier sitting right there. Notice I'm using the word possible. It's not definite, and in this particular case, I know with the univariate data, we could plug numbers into a formula and come up with it. Here, we don't really have an algorithm for it, and if we did, it might be a little bit more involved than we want it to be. So we'll say it's a possible outlier. We'll move on. The direction of this is definitely positive, and then that's a pretty strong relationship. That line pretty much catches all those points. Here's another example. So explanatory, the time swimming. The response would be the pulse rate. So this particular researcher wants to take a look at some type of relationship. Does the time swimming in minutes affect the pulse rate? The form of this, it does look linear, but as we notice, as you go down, right, it kind of spreads out as we move down that line. So that's probably worth noting, which we did right here, right? Scatter seems to increase as the time increases. So somehow we want to describe anything that looks a little out of the ordinary or different to us. The direction, definitely negative. And then this is probably more of a moderate in terms of strength, especially compared to our previous example. And we'll take a look at one more. So here, the explanatory would be the percent without the diploma. The response would be teacher pay. The form, there's really, it's not linear. It's just a large cluster of data. So one thing that you would want to put in here, this is not linear. That's definitely worth noting. Now, if you notice, hey, that looks kind of quadratic, that looks kind of exponential, you don't have to actually try to figure out what kind of curve fits it. You just have to say it's not linear. This doesn't have a direction, and the strength is very, very weak. As we start creating scatter plots, one of the big things that we want to look at is correlation. In terms of, we mentioned strength just a second ago, but correlation, what it does is it's going to allow us to actually kind of start to put a number with the strength of a relationship. So that is always represented by the letter R. Probably a lot of us have seen that before in previous classes as we've done linear regression. As a reminder, R can take on values from -1 to +1. And the closer we get to those two bounds, that's an indication of a strong linear relationship. Is not a guarantee, right? Anything near 0 basically tells us there's not a linear relationship, but you do need to be aware that you want to not only look at just the R value in conjunction with the actual graph, right? Look at the data. If you can graph it, whether it's in your calculator, whether by hand or whether you have a graph, look at that and look at R to start making your conclusions about how these things look. For us, so a correlation of 0, like I just said, there's really no way. I don't know where I would draw a line there. Probably just something like that. -3, we should start to see a downward trend, but it's still pretty scattered. 0.5, we should see an upward trend, right? And things are starting to kind of group together a little bit better if I were to try to draw a line of best fit. 0.7, again, or -0.7, excuse me, it's going down, and it's getting more and more concentrated. 0.9, we should see a very positive, very strong relationship all of a sudden, right? It's very easy to see that relationship. And then a -0.99, going downhill, but very, very tight. Now, in the real world, as people actually collect data out there, chances are you don't really ever get that 0.99 or that 0.9, really even a 0.7. Real world data a lot of times looks a lot more like this, where we can see there's a trend happening, but do we really know what it is? So speaking of that line of best fit, really what that's going to do, there's an algorithm to calculate it. And when you use your calculator to find the line of best fit or to find that equation, this is what your calculator is doing. It's essentially trying to draw that line, right? So we have this prediction line as close to as many of those points as possible. Well, how does it define how close? Well, you got this predicted value versus the actual value and this idea, this error, right? And what it's trying to do, if you can move this line kind of up and down, you can kind of imagine those squares would be getting bigger and smaller and bigger and smaller. And so the idea is we want to move this prediction line in such a way that we minimize the sum of all of these errors. In other words, we want to make all these squares as small as possible. And so we come up with a new term for this, which is called the least squares regression line, right? The LSRL, which is the exact same thing as your line of best fit. The equation for that is y hat equals a plus bx. A little bit different look than your normal y equals mx plus b, and there is a reason that we're going to use this form. A few facts about the least squares regression line is that every one will pass through x bar, y bar, right? This would be the mean of the x's. And then y bar, that's a new one, but this is just the mean of the y's. Right, we've got two variables now. You got x and y. So if we averaged all the x's, we get x bar. If we averaged all the y's, we get y bar. The relationship between slope and correlation. It's not that slope equals correlation, but there is a relationship here. The slope and the correlation also are affected by sy and sx. And if we remember what S was previously, this is just standard deviation. But this is standard deviation of the y's over the standard deviation of the x's. And if we think about this, standard deviation being a measure of spread, again, if things are very, very spread out, That probably tells us something about how related they are. But there's kind of this ratio. We're kind of comparing the spread, the vertical spread and the horizontal spread. We're combining that with R, and we're coming up with this value for B. Now, at the end of the day, you're not going to have to do these calculations. The calculator gives all this to you. But it's nice to see where things are coming from. This idea right here is very, very worth. Like, that's something that you definitely want to keep in mind, that every least squares regression line, if you plotted the x bar comma y bar as a point, your least squares regression line must pass through it. One last thing that you guys will be asked to do, and this is worth to go ahead and start thinking through. Um, these are a couple of your templates when you're going to be asked to interpret slope and to interpret y-intercept. Excuse me. Um, And what you can do with this, in an ideal situation, you know exactly what you're looking at, and you can kick this information back and you understand what you're looking at. But if you're not quite sure exactly what this is telling you, if you'll at least memorize these templates, you'll always get these questions right by filling in a few blanks. So instead of saying for every 1 unit increase, uh, in x, well, first thing we do is we'd replace the word unit here with whatever our actual unit is for this particular problem, and then go ahead and put in the x variable, whatever it is. So for us, one of the examples was number of powerboat registrations. The y in that case was number of manatees killed, and then you'd literally just replace the word slope with the number for your slope. Same thing with the intercepts. You literally take your x, so when the number of powerboats was 0, the number of manatees killed, and then you're literally just going to plug in that a value that you got from your least squares regression line equation. And this equation, along with all of this information, can be found in either two variable stats or the linear regression function, which is just below that. Um, and actually the one that you guys want to use is the 8th one. So you're going to have to bypass the 4th one, and that's probably the one that you're most used to. But all of this stuff is either found in 2var stats or the 8th one down on the list, which is linear regression, and it's linear regression in that form.